We will start this section with a brief overview of transmission lines and their general operation and characteristics in a power system. A transmission line is a circuit that is used to transmit power from one location to another. These transmission lines can span short distances of a few hundred meters to spanning very long distances in the magnitude of hundreds of kilometers. The two techniques of line protection we will address are distance relaying and line current differential. We will first look at distance relaying. Transmission lines that are protected using distance relays are usually at least 1 kilometer in length and can reach distances of 750 kilometers or more. Transmission lines consist of conductors that are supported by structures to hold the conductors high above the ground. These conductors are connected to the structure using devices called insulators. These insulators ensure that there is no electrical connection between the conductors and the supporting structure. The structures supporting the conductors can be constructed of wood, metal, or concrete. The material that is used in the structure, the physical arrangement of the components used, and the geography that the conductors and towers are located in greatly affects the electrical properties of the line. All of these factors must be considered when determining the best method of protecting the transmission line. In a power system, the area that constitutes a transmission line is defined by well-defined boundaries. This physical location of a line boundary is often called a terminal. The terminal can be a switch, a breaker, a bus, or a transformer. Transmission lines can be broken down into one of four main classifications that describe their configuration, the function they perform, and their location in the system. Parallel lines describe a configuration where multiple transmission lines run side by side. This is done to transmit large amounts of power from one location to another, in addition to providing a redundant path for power in case one of the lines were shut down due to a fault. Interconnector transmission lines are used to connect one section of a power system to another. Generator export transmission lines are used to transmit power from a generating station to the rest of the grid. Process plant load transmission lines are used to transmit power from transformers or switching stations to large industrial complexes. Transmission lines are classified into three categories that describe the presences of generation or possible sources of fault current that might be found at the transmission line's boundaries. These are single-ended, double-ended, and multi-ended. A single-ended line, also called a radial line, has a source at only one end. This type of line is used to deliver power from the source to a load at the other end of the line. Obviously, whenever a fault occurs, there is only one source of current to feed the fault. A double-ended line has only two boundaries, each of which can have a source of fault current available. This type of line is used to deliver power usually in different directions at different times. If a fault occurs on this transmission line, current will be fed to the fault from two locations. A multi-ended line has more than two boundaries, each of which can have a source of fault current available. At the time of a transmission line fault on this type of line, the direction of normal power flow can be highly variable, and the fault will be fed from many different locations. Sometimes the transmission line itself will be tapped to provide a source of power to a load. Distance protection is one method of protecting a transmission line in this configuration, and will be covered in detail later in this section. The voltages that are used for transmission of power over transmission lines are split into three categories. These are distribution levels, which are in the range of 2 kilovolts to 50 kilovolts, sub-transmission levels, which are in the range of 30 kilovolts to 150 kilovolts, and transmission levels which are greater than 100 kilovolts. Most applications that use distance protection are 50 kilovolts or greater. The lengths of transmission lines have also been classified into three categories. Short transmission lines are ones that are less than 80 kilometers in length. Medium transmission lines are ones that are roughly between 80 kilometers to 240 kilometers. Long transmission lines are ones that are greater than 240 kilometers in length. Shunt capacitance occurs between the transmission lines and the ground. This capacitance counterbalances some of the inductance by adding leading MVARs on the line and helps bring the current and voltage back to unity power factor. Typical three-phase MVAR values are 1.3 to 1.5 megavars per kilometer for 500 kilovolt lines and 0.15 to 0.4 megavars per kilometer for 230 kilovolt lines. Caution needs to be taken when transmission lines are used with high voltage potentials. Due to the Ferranti effect, the shunt capacitance on the line can become so large that the voltage on the far end of the line can rise higher than the normal line potential. The importance of transmission lines in a power system is quite evident. They are responsible for transmitting large amounts of current at possibly very high voltages. If a fault occurs on a transmission line and it is not cleared properly and quickly, the stability of the entire system can be compromised. The longer that the fault is allowed to remain on the line, the higher the possibility that the system will become unstable and possibly collapse. Calculating the magnitude of current that will flow through the transmission line at the time of the fault and configuring accurate settings for distance relays is a very important task that the protection engineer must perform in order to ensure the transmission line is properly protected. In order to do this, the protection engineer must first calculate the system impedance ratio and develop an equivalent electrical model of the transmission line. The system impedance ratio is a factor that needs to be considered when determining how to protect the transmission line and can greatly affect what will happen to a power system at the time of a fault. The system impedance ratio takes the source impedance of the system behind the transmission line and divides that by the line impedance that is being protected. If the system behind the transmission line has a strong source, the source impedance will be low. In this configuration, if a fault occurs on the transmission line, the fault current will be very high and the voltage will tend to remain stable. If the system behind the transmission line has a weak source, the source impedance will be higher. In this configuration, if a fault occurs on the transmission line, the fault current will be lower in magnitude and the line voltage will tend to drop. As you can see, the system impedance ratio is a very important factor in the stability of a power system. At the time of a fault, it must be considered when determining the type of protection needed and the speed at which the faults need to be cleared by relaying. When the current or voltage levels need to be accurately calculated at a specific point on the line, the protection engineer needs to draw an equivalent model of the transmission line. Different models of transmission lines are used for different lengths of line. These models are in three categories: short, medium, and long lines. The pi model shown here was historically used by the protection engineer to represent medium-length lines. However, by using this representation of the line, in addition to computer-aided software now readily available, the protection engineer can accurately calculate all required values for both medium and long transmission lines. This data simplifies the protection engineer's task in performing fault calculations to set up the distance protection within a relay. Each component in a power system, whether it is a source, a transmission line, or a load, has an impedance. This total system impedance limits the magnitude of current that will flow through the power system. In the power system seen here, we have a total system impedance of 230 ohms. If the source were generating power at 230 kilovolts phase to neutral, 1,000 amps of current would be supplied to our load. If a fault were to occur on the power system in a location that would cut off the path of current flow to the load, the total impedance of our power system would change to only 23 ohms. Due to the drop in impedance, our current level would now increase substantially. The operating principle of distance protection for transmission lines works in the following way. The magnitude of current and voltage is measured at the beginning of the transmission line, and using these measurements calculates a ratio of the voltage over the current. This ratio will then give you a value that is equal to the impedance of the total power system. When a fault occurs on the power system, thus cutting off the path of current to some of the load, the impedance of the power system will decrease. This decrease in impedance will cause the current to increase and the voltage to decrease slightly, thus changing the ratio of the voltage over the current to match the new impedance of the line. The voltage will decrease because the only voltage drops now occur across the transmission line and the source impedance. In this example, the fault is located after the transmission line, but before the majority of the power system load. Now the only impedance on this power system is the impedance of the source and the transmission lines before the fault. When this fault occurs, the current flowing through the transmission line will increase. The ratio of voltage over current, or impedance, will now significantly decrease. Distance relays are programmed to know the impedance to the end of the transmission line. If the impedance the relay calculates is less than the impedance of the transmission line, the relay knows that the fault is on the transmission line itself and must trip the circuit. By comparing the calculated impedance of the transmission line with the known impedance of the transmission line, you can determine how far along the transmission line the fault occurred, leading to the term distance or distance relaying. In this example, the current increased as a result of the reduction in impedance from 20 to 10 ohms, indicating that the fault occurred at a distance of 50% of the distance from the measurement point to the end of the transmission line. The impedance of the line is often drawn on an RX diagram. The x-axis represents the resistive component of the impedance of the line. The y-axis represents the inductive component of the impedance of the line in the positive direction, and the capacitive component of the impedance of the line in the negative direction. The impedance of a transmission line is inherently mostly inductive. Therefore, if you were to plot the impedance of the line on this graph, it would be very close to the y-axis. If you were to draw a line from this point to the origin of the graph, you would have a representation of your entire transmission line. For example, plotting a point on the line midway between the origin and the end of the line would give an impedance of 10 ohms. This would also be the impedance of the midpoint of the transmission line. In a normal power system, there is a load at the end of the transmission line. Typically, this load is mostly resistive and is also larger than all of the other impedances of the power system. Therefore, if you were to plot the impedance of a power system under normal conditions on an RX diagram, the point would be shown very close to the x-axis. The distance from the origin would be the magnitude of impedance of the transmission line and the load. If a fault to the ground were to now occur at the midpoint on the transmission line, all of the impedances after the point of fault would no longer be part of the power system. The impedance of the system would now only be the impedance of the source plus the impedance of the part of the transmission line before the fault. Since the power system impedance is no longer mostly resistive because the only impedance is now the transmission line, which is mostly inductive, the plotting of the measured impedance on the RX diagram will be very close to the y-axis. The impedance point will actually fall along the line drawn from the origin to the impedance of the entire transmission line. Since the distance that the relay measures to the fault is actually closer than the length of the entire transmission line, the fault is in the zone that the relay is protecting. Therefore, the relay will send a signal to trip the breaker to clear the fault. The trip of a transmission line breaker normally initiates an auto-recloser sequence that works in conjunction with the synchrocheck function. The auto-recloser and synchrocheck functions are covered in detail in the distribution section of the CD. To program distance relays, you need to configure the impedance of the line, where any impedance less than this value will indicate a faulted line. This is done in modern distance relays by creating zones of operation on the RX diagram. If the impedance calculated at the point of measurement of the power system ever falls within this zone, the relay will trip. These zones fit into the following operating characteristics: an impedance zone, an admittance or Mohs circle zone, a reactance zone, a resistance zone, and a quadrilateral zone. Let's take a look at each of these operating characteristics for distance relaying operating zones. First, we will discuss the zone of protection known as an impedance zone. Any impedance that falls within the radius of the circle indicates a fault that needs to be cleared. The reach indicates in ohms how far on down the power system the zone of protection extends. This type of zone is inherently non-directional and will detect faults that occur in the reverse direction away from the point of measurement. This type of zone is normally used for generator backup protection. The zone of protection shown here is known as a reactance zone. This type of zone is used to detect when the impedance of the fault has a very high resistive component in it. If the fault does have a high resistive impedance, this indicates that there is a load on the transmission line, and the fault is most likely not on the transmission line. This type of zone is usually never used to trip a transmission line on its own, but is normally used to supervise another distance zone of protection. For example, if an impedance zone detected the impedance of the line entering its zone of protection due to an external fault, the reactance zone can be used to block the impedance zone from tripping because it can determine that the impedance is mostly resistive, and therefore the fault is not on the transmission line. The next zone of protection we will look at is a resistance zone. This type of zone is used to detect when the impedance of the fault has a very high inductive component in it. If the fault does have a high inductive impedance, this indicates that there is very little or no resistive load at the end of the transmission line, and it is likely that the fault is located on the transmission line. This type of zone is usually never used to trip a transmission line on its own, but is normally used to supervise another distance zone of protection. For example, if an impedance zone detected the impedance of the line just slightly enter its zone of protection due to a fault occurring towards the end of its zone of protection, the resistive zone can be used to verify that the fault is actually on the transmission line, because the impedance of the fault is mostly inductive. In this configuration, the resistance zone would be giving the impedance zone permission to trip. The next zone of protection is the admittance zone, or Mohs circle zone. A Mohs circle zone is the most common type of protection zone that is used in transmission line distance relays. A Mohs circle zone detects whenever the impedance of the transmission line falls within the area defined by the circle. This type of zone is inherently directional and will not detect faults that fall in the reverse direction of the transmission line, since that point will fall outside of the circle. The reach of the zone of protection shows in impedance how far down the transmission line this zone of protection will protect. This reach always lies along the line of the impedance of the transmission line, which is usually around 75 to 80 degrees away from the x-axis. The reach is also the point in the circle that is the farthest away from the origin of the graph. One of the reasons that the Mohs circle is positioned where it is along the graph is so the zone of protection will not trip on a power system that is highly loaded. For example, on the power system seen here, the reach of our Mohs circle was programmed to be 18 ohms. Under normal circumstances, where there are no faults on the power system, the impedance of the power system will be very large, and the plotted measured impedance on the Rx will be located close to the x-axis. If a substantial amount of load were now added to the power system, the current needed to feed the load would increase substantially, as seen here. Even though there is no fault on the transmission line, the newly calculated impedance of the line would be less than the reach of the Mohs circle zone. However, since the load that was added is mostly resistive, the plotted impedance point would be much closer to the origin of the graph, but still very close to the x-axis. Since the Mohs circle is positioned where it is on the graph, there is very little area included in the zone of protection in the resistance direction. Therefore, the new impedance will not fall into its zone of protection, and the relay will not trip. Many advanced microprocessor-based relays, such as the URD60, gives the user the ability to further customize the shape of the Mohs circle to meet their protection needs. For example, if this power system has instances where it can be heavily loaded, which may cause the impedance of the line to encroach into the Mohs circle, the area of the circle may need to be changed to not include this area in the zone of protection. The Mohs zone can be altered to form a lenticular shape, which looks at the magnitude of the impedance and only allows tripping when the impedance falls very close to the angle of the transmission line impedance. Therefore, highly loaded systems which cause the impedance point to approach very near the origin will not result in tripping the transmission line. As a side note, the D60 relay also gives the protection engineer the ability to configure the Mohs characteristic into what is known as a tomato-shaped zone. A tomato-shaped Mohs characteristic allows for faults that have more of a resistive element to fall into its zone of protection. Another custom zone is known as a quadrilateral zone of protection. This type of zone allows you to set the reactance and resistive upper and lower boundaries to create your own custom shape to match the needs of your power system. In this type of zone, there are essentially two reaches, one in the inductive direction and one in the resistive direction. Some advanced distance relays have added features to the Mohs circle characteristic to increase security and reliability for faults that occur very close to the point of measurement, which is at the beginning of the transmission line. Again, this point of measurement is shown at the origin of the RX diagram. On faults that occur very close to the point where the currents and voltages are being measured, some relays may have difficulty distinguishing whether the fault is inside or outside their zone of protection. To overcome this difficulty, the relay can change the size of the Mohs circle when the calculated impedance is very near the origin. This is sometimes referred to as an enhanced Mohs element. If a fault occurs just before the beginning of the transmission line, and the transmission line is double-ended or multi-ended, current will flow into the CT from the opposite direction. If the relay now calculates the impedance of the line, the value will be negative, and plotting that impedance point will put it very near the origin, but in the reverse direction to the transmission line. To make sure that the Mohs characteristic does not mistake this as being an internal fault, the relay recognizes the low impedance of the line, sees that the value is negative, and shrinks the radius of the circle. Since the Mohs circle is no longer near the origin and the location of the fault, there is no chance of the relay false tripping. Notice, however, that the reach of the Mohs circle did not change, and still extends out to the end of the original zone of protection. If a fault occurs just after the beginning of the transmission line, current will flow into the CT from the positive direction. If the relay calculates the impedance of the line, the value will now be positive. Plotting that impedance point will put it very near the origin in the positive direction of the transmission line. To make sure that the Mohs characteristic does realize this as being an internal fault that needs to be cleared, the relay recognizes the low impedance of the line, sees that the value is positive, and enlarges the radius of the circle. Since the Mohs circle now extends past the origin to include a larger area, The location of the fault is sure to fit in the zone of protection. Therefore, the fault can be cleared properly. Notice, however, that the reach of the Mohs circle did not change and still extends out to the end of the original zone of protection. We will now highlight some of the distance protection features that are available in more advanced distance relays, such as the GE Multilin D60. These relays will have both ground and phase distance protection elements available. The ground distance elements will detect faults between a phase and ground, while the phase elements will detect faults between phases. For both of these types of elements, there are 4 zones of protection available. Every zone of protection can be programmed to be protecting in the forward or the reverse direction of the transmission line. These zones can also be programmed to have a Moh or quadrilateral shaped protection characteristic. The operating characteristics of each zone can also be set individually. A distance protection relay is used to detect and clear faults that occur on a transmission line. It accomplishes this type of protection for both the phase and ground distance elements by measuring the current and voltage, and using this information, calculates the impedance of the line. If the measured impedance is less than the known impedance of the line, this indicates the line is now shorter than expected, indicating it is faulted. However, due to the inherent inaccuracies of CTs and VTs, the impedance calculations made by the distance relays cannot be guaranteed to be extremely accurate. For example, let's assume the actual impedance of our transmission line is 20 ohms. A fault occurs just past this transmission line on the next adjacent circuit. The actual impedance from the measurement point of the relay to this fault is 20.5 ohms. Due to the inaccuracies in the CTs and VTs, along with some transient effects, the relay may measure the impedance to the fault to be less than it actually is, and see the fault as being on the transmission line it is protecting. This would cause the relay to trip the circuit breaker and shut down this transmission line when it did not need to. Because of these inaccuracies, distance zones of protection are not set to stop right at the boundary of a transmission line. Distance relays use multiple zones of protection, with some of them set short to only protect part of a transmission line, and others set longer to protect the entire length of a transmission line, plus some of the next adjacent line. The zones of protection that are set to cover only part of a transmission line are said to be underreaching. The zones of protection that are set to cover more than just that relay's transmission line are said to be overreaching. Zones of protection can also be programmed to protect in either the forward direction or reverse direction. Zones that are set to protect in the forward direction are said to be looking into the line, while zones that are set to protect in the reverse direction are said to be looking out of the line. The strategy used to protect a line is commonly referred to as a scheme. All protection schemes used in distance relaying fit into one of 2 categories: pilot-aided and non-pilot-aided schemes. The main difference between the 2 types of schemes is that the distance relays used in pilot-aided schemes communicate with each other to determine whether the fault is located on the transmission line or not. The relays used in non-pilot-aided schemes do not communicate with each other and instead use delays and other forms of coordination to determine whether the fault is located on the transmission line or not. All coordination in these schemes is done within each individual relay itself. In the category of non-pilot-aided distance protection schemes, there are 2 main types that we will discuss. These are the stepped distance protection scheme and the Zone 1 extension scheme. We will first describe the stepped distance scheme. This scheme is the basic structure for all other distance schemes, so it is important to cover it in great detail. The stepped distance scheme uses 4 different zones of protection to protect its own transmission line, and to act as a backup distance relay to protect transmission lines that are located next to it. We will use the power system shown here to describe how the 4 zones of protection are set and used. The main transmission line we will be protecting will be transmission line number 1, and the relay will be located at the far left of that line. The first zone of protection is set to underreach and extends from the beginning of the transmission line to 80 or 90% of the length of the entire line. This zone is also set to have no time delay. Therefore, if a fault occurs in this zone, the relay can be sure that the fault is located on its transmission line and can trip immediately. Zone number 1 will not protect the last 10 to 20% of the line, which is known as the end zone. Any faults that occur in this area will not be seen by zone number 1 and will have to be cleared by one of the other zones of protection. The second zone of protection is set to overreach and extends from the beginning of the transmission line, past the end of the line, and into the next adjoining transmission line. This is called Zone 2. Zone 2 is usually set to 120% of the impedance of the transmission line. Zone 2 is set in this manner so that it can detect faults that occur in the end zone area that zone number 1 cannot detect. Zone 2 is also always programmed to have a time delay set between 0.25 and 0.4 seconds. Using all of the characteristics we have just discussed, Zone 1 and Zone 2 have the ability of protecting the entire length of the transmission line in the following way. Any faults that occur at the beginning of the transmission line will be picked up by both Zone 1 and Zone 2, as seen by the status of their pickup flags. Since Zone 1 has no intentional time delay, its operate flag will turn on immediately. The Zone 2 operate flag will not yet turn on because it has a time delay programmed within it. The Zone 1 operate flag will then trigger the relay to trip to clear the fault. At that point, the fault will be cleared. The Zone 1 pickup and operate flags will turn off. The Zone 2 pickup flag will turn off, and the Zone 2 operate flag will stay in the off state, with never having turned on. On another occasion, if a fault occurred in the end zone region of the transmission line, the two zones would act differently. The fault does not lie within the zone of protection of zone number 1. Therefore, Zone 1 will not pick up. The fault does lie within the zone of protection of zone number 2. Therefore, Zone 2 will pick up. After the Zone 2 time delay has expired, the Zone 2 operate flag will change to the on state and trigger the relay to trip and clear the fault. Once the fault is cleared, both the pickup and operate flags of Zone 2 will turn off. You may be wondering what would happen if a fault occurred on the adjacent transmission line, but still within the Zone 2 area of protection. Normally, after the Zone 2 time delay expired, the relay would trip the unfaulted transmission line. However, you have to remember that every adjacent transmission line is protected by its own distance relay. This fault would fall into the second relay's first zone of protection, and the fault would be cleared before the timer of Zone 2 in the first relay expired. The third zone of protection is set to overreach past the end of the second adjacent transmission line. The third zone is used to act as a backup for that next adjacent transmission line in case the protection on that transmission line fails. For this reason, Zone 3 is usually set to extend to the same point as Zone number 2 of the adjacent transmission line, so a setting of 220% of the impedance of its own transmission line is often selected if Line 1 and Line 2's impedances are the same. Zone 3 must have a time delay that is longer than the operate time of Zone number 2 of the adjacent transmission line. A time delay of 1 second is commonly used. Zone 4 is used as backup protection for a small portion of the adjacent transmission line in the reverse direction. The operation of this zone is usually time delayed to allow the first zone and second zone of that adjacent transmission line to operate first. A time delay of 750 milliseconds to 1 second is common. Once each of the 4 zones have been set, the step distance scheme to control the breaker on the left side of the transmission line is complete. However, the breaker on both ends of the transmission line must be opened to completely clear a fault. Therefore, another distance relay must be located on the right end of the transmission line to control that breaker. The relay on the right needs to be programmed with the same characteristics as the relay on the left. However, this one will be set up to be protecting in the opposite direction. Now, the zones of protection of each relay will detect any faults that occur on our protected transmission line. These relays will then proceed to open the breaker and clear the fault from their own respective end of the line. Each relay will also have ground stepped distance zones of protection, which are identical to that of the phase stepped distance zones. The difference being that the ground distance elements are used to detect single phase to ground faults. The other type of non-pilot aided scheme we will discuss is the Zone 1 extension scheme. The Zone 1 extension scheme is an enhancement to the stepped distance scheme covered in the previous section. This protection scheme operates on the principle that most transmission line faults are transient in nature, which means the fault is not permanent. For example, the most common cause of faults on transmission lines is lightning. If lightning strikes a transmission line, it ionizes the air, which reduces the resistance between the different phases of the line. This reduced resistance allows for a path for current to flow, and hence creates a fault. Once the transmission line is tripped and the fault is cleared, the ionized air is removed and there no longer exists a path for current to flow. Closing the transmission line circuit breaker at this point would re-energize the line and transmission of power could resume. As mentioned before, the Zone 1 extension scheme is like the stepped distance scheme where it has 4 zones of protection. The difference between the two schemes is that in the Zone 1 extension scheme, an additional Zone 1 impedance setting is set higher to overreach into the next adjacent transmission line. The impedance of this extended Zone 1, which is labeled Z1X, is usually set to the same impedance as the Zone 2 setting of 120% of the impedance of the entire transmission line. This extended Zone 1 is used by the distance relay until it detects a fault within this zone of protection. Once a fault is detected, the relay will immediately trip the transmission line since there is no delay in the operation in the extended Zone 1 element. As you can see, the relay will trip the line even though the fault may exist in the area located in the extended Zone 1 but be in the adjacent transmission line. Once the breaker is opened and the fault is cleared, the relay will then automatically reclose the breaker and re-energize the transmission line. Once the line has been reclosed, the relay will then use the standard Zone 1 characteristic and now underreach to only protect an area within its own transmission line. If the fault that occurred was a permanent fault and the fault is located within the transmission line's newly shortened Zone 1, the relay will trip and again open the circuit breaker to clear the fault. If the fault was transient in nature, the first occurrence of tripping the line would have removed the fault and transmission of power would resume. If the fault that occurred was a permanent fault and reappeared after the reclosing, but was not located in the new shortened Zone 1 protected area, the relay would not pick this up for a second time in Zone 1 and not trip to try to clear the fault. The permanent fault would then be cleared by the Zone 2 protection after the set time delay if the fault fell inside the transmission line's end zone area. If the permanent fault was picked up by the relay Zone 2 because it was located at the beginning of the next adjoining transmission line, the relay protecting that transmission line would pick it up in its Zone 1 of protection and clear the fault. The disadvantage of the Zone 1 extension scheme is that external faults within the extended Zone 1 reach of the relay trip the breaker instantaneously, even if that breaker did not need to be tripped. This needless tripping increases the amount of breaker maintenance needed and causes a needless loss of power supply to some customers. All transmission line distance protection schemes that fit into the category of pilot-aided schemes are based on the basic concept of stepped distance protection schemes. On a stepped distance scheme, any fault that occurs in the midpoint of a transmission line that fits into both of the relay's Zone 1 will be cleared instantly by the relay located at each end of the line. However, if the fault is located on one of the end zones of the transmission line, which is also known as a close-in fault, it will not be cleared instantly at both ends of the transmission line. The fault will be cleared instantly by Zone 1 of the relay that is located near the fault, but will not be cleared instantly by the relay at the far end of the line because the fault did not fall in its Zone 1. The fault will not be cleared at the far end of the transmission line until the time delay in Zone 2 of that relay has expired. You'll remember that the time delay for Zone 2 operation is usually in the range of 250 to 400 milliseconds. The main reason to modify and improve upon the stepped distance scheme using pilot-aided schemes is to speed up the performance of clearing faults that occur in this end zone of the transmission line. Pilot schemes speed up the clearing of faults that occur on the transmission line and inside Zone 2 of the local relay by communicating with the relay at the remote end of the line to determine if the fault is actually on the transmission line. Therefore, all pilot-aided schemes require a communication channel be provided between the two relays. Over this communication channel, the two relays share information regarding the general location of the fault, allowing the clearing of faults on the transmission line to occur as fast as possible. The most common pilot-aided schemes are the DUTT scheme, which stands for Direct Underreaching Transfer Trip, the PUTT scheme, which stands for Permissive Underreaching Transfer Trip, the POTT scheme, which stands for Permissive Overreaching Transfer Trip, the Hybrid POTT scheme, which stands for the Hybrid Permissive Overreaching Transfer Trip, and the Directional Blocking scheme. We'll discuss all of these schemes in the following sections. A fault that occurs in the end zone of a transmission line normally will not be fully cleared until the time delay of the Zone 2 protection element has expired. The DUTT scheme, which stands for the Direct Underreaching Transfer Trip scheme, is used to reduce the amount of time needed to wait before clearing a fault that occurs in this end zone of a transmission line. As for all pilot schemes, there must be a communication channel set up between the distance relays at each end of the line. This communication channel can be one of many different configurations. The communication channel may have the ability to only send one bit of data back and forth between the relays, such as a power line carrier communication link. or may be able to send multiple pieces of data back and forth between the two relays, such as a fiber optic or microwave link. First, each of the relays must also have all of its 4 zones of protection set up to operate as a standard stepped distance application. For the examples we will be using in this section, we will label the 2 distance relays that are protecting the transmission line in the following way. The distance relay that is located on the left side of the transmission line will be called the local relay. The distance relay that is located on the right side of the transmission line will be called the remote relay. When a fault occurs in the middle of the transmission line using the DUTT scheme, or both zone 1s of the local and the remote relays, the relays will trip and clear the fault instantly at both ends of the line. This is similar to the stepped distance scheme. Faults that occur in the local relay's end zone of the transmission line will be cleared at the remote end of the line instantly by the zone 1 element of the remote relay. The breaker at the local end of the line would normally not trip until the timer of zone 2 had expired. Using the DUTT scheme, if a fault occurred in the transmission line end zone, the remote relay that identified the fault in its zone 1 will immediately trip the breaker on its side of the line. Upon detecting this fault in its zone 1, the remote D60 will also immediately send a signal, which is known as a key, over the communication channel to the local relay located at the other end of the line. This is where the term underreaching came from, because the keying signal is initiated by identifying a fault within the relay's underreaching zone 1. As soon as the local relay receives the DUTT key from the remote relay, it will immediately trip its breaker, thus clearing the fault on the transmission line. The important thing to note with this scheme is that the local relay will trip as soon as it gets a transfer trip signal from the remote relay, without requiring any indication of a fault within its own zones of protection, hence the term direct transfer trip. The PUTT pilot-aided scheme stands for the Permissive Underreaching Transfer Trip Scheme. Just like the DUTT scheme, the PUTT scheme is used to speed up the clearing of faults that occur in the end zone of a transmission line. For this scheme, as for all pilot-aided schemes, a communication channel must be provided between the 2 relays located at each end of the transmission line. In the PUTT scheme, the remote distance relay sends a PUTT key signal to the local relay whenever it detects that a fault exists within its underreaching Zone 1 area of protection. This is where the expression underreaching comes from in the term permissive underreaching transfer trip. The difference between the DUTT scheme and the PUTT scheme is what the local relay does when it receives the key signal from the remote relay. In the DUTT scheme, the local relay trips as soon as it received the key signal. In the PUTT scheme, the local distance relay PUTT logic will now only trip the breaker if it receives the PUTT key and the local relay has detected a fault within its Zone 2 area of protection. If the local distance relay received the PUTT key and it does not detect a fault within its Zone 2 area of protection, the PUTT scheme will not cause the local distance relay to trip. Therefore, the distance relay's PUTT scheme uses the key from the remote relay as a permissive signal that allows it to trip if the local relay detects a possible fault on the transmission line. Hence the term permissive underreaching transfer trip. When a fault occurs on a transmission line somewhere on the line, currents are flowing to ground. Measuring the direction of the flow of the ground current is used to assist some of the pilot-aided distance protection schemes in determining if the fault and the source of the ground current are located on their transmission lines. The ground directional overcurrent elements let the pilot-aided schemes know if the ground current rises above a minimum set level, and if it does, what direction the ground current is flowing. The ground directional overcurrent elements are used by the pilot-aided schemes because they are sometimes more sensitive to detecting faults than the distance elements are when the source has a weak infeed or high system impedance ratio. The benefits of using ground directional functions in pilot schemes are that the zero sequence and negative sequence currents that are used to detect the direction of ground currents do not contain very many load components. Therefore, the pickup levels for the ground directional elements can be set very low and thus are very sensitive. The ground directional elements are also very fast operating because the zero sequence and negative sequence currents build up from practically a zero pre-fault value. Also, since there was no ground current before the fault, the pre-fault zero sequence and negative sequence currents do not bias the direction of the developing fault components. The POTT pilot-aided scheme stands for the Permissive Overreaching Transfer Trip Scheme. Like the other pilot-aided schemes, it is used to speed up the clearing of faults that occur in the end zone of a transmission line. Again, a communication channel must be provided between the two relays for the POTT scheme to operate. In the POTT scheme, the remote distance relay speeds up the tripping of an end zone fault by sending a permission to trip key from the remote relay to the local relay under two conditions. The first condition is when the remote relay detects a fault occurring within its overreaching zone 2. This is where the expression overreaching comes from in the term permissive overreaching transfer trip. The second condition under which the remote relay will send a permissive key is when it detects that ground current is flowing in its forward direction. Therefore, the remote relay's forward negative sequence directional overcurrent element, or its forward neutral directional overcurrent element's operation, will also cause the remote relay to send a POTT key to the local relay, in addition to the overreaching Zone 2 pickup flag. In the POTT scheme, the local relay POTT logic will only cause the breaker to trip if it gets the POTT key and the local relay has detected a fault within its Zone 2 area of protection, or it detects that ground current is flowing in its forward direction if this function is enabled. As a result, either the local relay's forward negative sequence directional overcurrent element or the forward neutral directional overcurrent element, as well as the picking up of a Zone 2 fault, will cause the POTT scheme to trip the breaker once it has received a permissive key from the remote relay. Any combination of the two reasons the remote D60 sends transmit keys and the two reasons the local relay identifies a fault will isolate the transmission line and verify the fault is located on the transmission line we are protecting. As shown in Diagram 1, if Zone 2 of both relays identifies a fault, it is a clear indication that the fault is on the transmission line, so both relays will trip their respective breakers. In Diagram 2, the remote Zone 2 indicates that the fault is located to the left of the remote relay, and the forward flow of ground current, as seen by the local relay, indicates that the fault is to the right of it. Therefore, the fault is on the transmission line, and both relays will trip their breakers. In Diagram 3, the forward-flowing ground current of the remote relay and the Zone 2 picking up on the local relay is a clear indication that the fault is on the transmission line, and so both breakers will be tripped. Finally, in Diagram 4, the direction of ground current detected by both relays is flowing into the transmission line, which is again a clear indication that the transmission line is faulted, resulting in the tripping of both breakers. The hybrid POTT, or hybrid permissive overreaching transfer trip scheme, is a modification of the POTT scheme, which adds an extra degree of security and additional protection for transmission lines that have a weak in-feed source. The hybrid POTT scheme works in the very same way as the POTT scheme to speed up the clearing of end zone faults. In this scheme, both a Zone 2 fault and forward-flowing ground current being detected by the remote distance relay will send a permissive key to the local distance relay, thus allowing it to trip. The local distance relay also tries to detect reverse ground current or a Zone 4 fault. If either reverse ground current or a fault is picked up in Zone 4, the hybrid POTT scheme is blocked from tripping, resulting in additional security. The other advantage of the hybrid POTT scheme over the POTT scheme is its ability to trip on faults that are fed by a source that has a high source impedance. This is also referred to as a weak in-feed. When a fault occurs on the transmission line with a weak in-feed that is located close to the local distance relay, the characteristics of the transmission line will operate in the following way. The voltage measured by the local distance relay will be very close to zero. The current flowing through the local distance relay CTs will not be very high. Therefore, the distance zones of protection may not pick up because the fault current is below the current supervision level, as was discussed in the zones of protection section. Also, the zero sequence and negative sequence current will be almost zero. Therefore, the forward and reverse ground directional overcurrent elements will not operate. Even though none of the distance relay's protection elements have picked up the faulted line still needs to be cleared. The weak in-feed feature of advanced distance relays can detect this condition and correctly trip the relay. The directional blocking scheme is one of the most popular types of teleprotection schemes used in distance applications today. Again, we should state that the purpose of the scheme is to speed up the tripping of faults that occur in the end zone of a transmission line. As with all pilot-aided schemes, a communication channel must be provided between the two relays located at each end of the transmission line for the directional blocking scheme to operate. In the directional blocking scheme, the local distance relay has an additional delay timer that is started by the detecting of either a fault inside its Zone 2 area of protection, or the detection of ground current flowing in the forward direction. This timer is set considerably shorter than the normal Zone 2 delay. When this additional timer expires, the local distance relay will trip the local breaker unless it receives a block message or key from the remote distance relay. The remote relay will only send this blocking key if it detects that the fault is located in its Zone 4 area of protection, or it detects that ground current is flowing in the reverse direction, both of which would indicate an external fault. The last subject we will deal with in distance relaying is power swing blocking. A stable power swing can be seen as a condition where our system loses synchronism for a short period of time with our neighboring system, and then later regains synchronism. Two reasons that a power swing such as this can occur are: one of the systems loses a significant amount of generation, therefore instantly becomes much weaker, and the load of the system remains constant, or the system is already weak, and the load suddenly increases substantially. During a power swing, the voltages and currents will fluctuate significantly, drastically affecting the value of the measured impedance of the line. The plotted impedance as measured by the distance relay will slowly swing from our load point into the distance operating zones, and then back out to a load point if system regains synchronism. The power swing blocking feature on advanced distance relays can detect that the impedance swing is a recoverable power swing, and will block the distance zones from operating. This is detected by creating an additional impedance zone located around the operating impedance zones as shown. A stable power swing is detected if the impedance of the system moves into this new impedance zone for an extended period of time. Under this condition, the distance protection will be blocked. If this swing were a real fault that entered the power swing blocking area, it would move very fast through this additional area and into the operating impedance zone. The power swing blocking characteristics must be configured to be much larger than the distance Zone 1 characteristic to ensure a stable power swing is detected long before Zone 1's operating characteristic is reached. The outer boundaries of the two larger zones in this diagram form a tomato-shaped zone, while the area of overlap of these two zones form an inner lens-shaped zone. The resulting tomato-shaped outer zone is what is used to detect the presence of a power swing and sets the block of the distance element. If the impedance enters the lens shape, the relay no longer sees this as a power swing, but maintains the block signal for a short time to allow the system impedance to leave this area, as will happen in a stable swing. With the advent of high-speed, low-cost LAN technology, a new form of line protection known as line current differential relaying is becoming more popular due to its speed, sensitivity, immunity to power swings, and being a form of unit protection. Unit protection means the zone of protection covers the complete power system component without overreaching. Line current differential relaying measures and compares the current at both ends of the line using two separate relays and a communications link. The zone of protection is the segment of the line between the two sets of CTs. Theoretically, the sum of the two currents should be zero. If there is a difference beyond a reasonable amount, there is a fault on the line, and so both relays trip their respective breakers, isolating the line. The communication link requirements for differential relaying can be quite modest by today's standards. For example, the GE Multilin L90 current differential relay requires only a 64 kilobytes per second communication link. To enhance reliability, modern utility class line current differential relays will provide built-in distance backup in the event of a communication link failure. For the following examples, we will be using the GE Multilin L90 relays. Let's first take a look at a two-terminal application to better understand the operation of line current differential relaying. Upon power-up, the two relays first synchronize their internal clocks via the communication link. Each relay then measures the current at its CTs and sends this information along with a timestamp to the other relay. Using a form of the percent differential element, each relay compares the current measured at its location with a value of current having the same timestamp that was received from the remote location. If there is more than an acceptable error, there is a fault on the line, and the element in both relays will operate to isolate that section of line from the rest of the power system. The L90 relays support both 2 and 3 terminal configurations. The relays in a 3-terminal configuration will behave in the same fashion as the 2-terminal configuration, with each relay making its own decision as to whether it will trip. In this way, all L90 relays are said to act as masters. If there is a failure of one communication channel path, the relays will automatically switch to a backup master-slave mode. The relay that is still in communication to the other two relays will be the master, and the other two will switch to slave mode. The master relay will perform the differential element calculations for its location and both of the slave locations. If a fault occurs, the master will either trip its own breaker and/or send the appropriate signal to one or both of the slave relays to clear the fault. With line current differential relaying, there are two common types of transfer trips that can be sent: the 87L direct transfer trip and the key direct transfer trip. The 87L direct transfer trip is sent from the master's line differential element and causes the slave that receives the transfer trip to trip. The key direct transfer trip is sent by another function, such as breaker failure. The basic premise for the operation of differential protection schemes is that the sum of the currents entering the protected zone is zero. In the case of a power system transmission line, this is not entirely true because of the capacitive charging current of the line. For short transmission lines, the charging current is a small factor and can be treated as an unknown error. In this circumstance, the relays can be applied without voltage sensors. The line charging current will be included as a constant term in the total variance, increasing the differential restraint current. For long transmission lines, the charging current is a significant factor and should be calculated by the relay to provide increased sensitivity to fault current. Compensation for charging current requires that the voltage at the terminals is supplied to the relays. The algorithm calculates the capacitance times the change in voltage over the change in time for each phase, which is then subtracted from the measured currents at both ends of the line. This is a simple approach that provides adequate compensation of the capacitive current at the fundamental power system frequency. Traveling waves on the transmission line are not compensated for and contribute to restraint by increasing allowable error in the setting of the differential error. If the VTs are connected in Y, the compensation is accurate for both balanced conditions. For example, all positive, negative, and zero sequence components of the charging current are compensated. If the VTs are connected in delta, the compensation is accurate for positive and negative sequence components of the charging current. Since the zero sequence voltage is not available, the relay cannot compensate for the zero sequence current. Let's look at an example of a breaker failure protective element. In this example, the protective relays operate correctly, but the associated circuit breaker fails to clear the fault because of some malfunction within the breaker or its control circuits. The fault will now remain on the system until some other means is used to clear it. In our example, the primary or backup relays start a timer once a fault has been detected. The timer will then time out and send a trip signal to all breakers that can feed the failed breaker with power.